This research paper, authored by Zhang and Zhang, explores the convergence of finite element methods on arbitrary meshes, with a particular focus on the weak Galerkin (WG) method. The authors demonstrate that the WG method converges to the true solution in both triangular and tetrahedral meshes, even when these violate the maximum angle condition. This is a significant departure from standard conforming, nonconforming, and discontinuous Galerkin finite elements, which do not converge under such conditions. The paper begins by introducing the concept of convergence in unidimensional finite element computation, where discrete solutions converge to the true solution as the size of the largest interval decreases. However, this does not hold true in higher dimensions, as demonstrated by the example of Babushka and Aziz in 4, where finite element solutions failed to converge on certain patterned triangular meshes that violate the maximum angle condition. To illustrate this problem further, the authors provide two examples from calculus. In the first example, approximating a circle with polygons, the arc length of the polygon converges to the circumference of the circle as the longest edge size decreases. In the second example, they approximate a cylinder using linear triangles with both horizontal and vertical sizes approaching 0. Despite the distance between the cylinder and the triangles decreasing, the total area of the triangles converges to a number different from the surface area of the cylinder. This is due to the small triangles maintaining an angle to the cylinder, failing to approach the tangent planes to the surface. The authors then delve into the details of the WG method, which they claim converges on arbitrary meshes. They present the 2020 mathematics subject classification as primary, 65N15, 65N30, and list key words and phrases such as discontinuous finite element, maximum angle condition, mixed finite element, Stokes equations, and tetrahedral grid. The paper also includes numerical tests that confirm the theoretical findings. In conclusion, this paper presents a novel approach to finite element methods using the WG method, which can achieve convergence on arbitrary meshes, including those violating the maximum angle condition. This research contributes significantly to the field of numerical analysis and has implications for various applications in engineering, physics, and computer science. Traditional finite element methods struggle to accurately approximate curved surfaces, such as cylinders, using triangular meshes. As the mesh size approaches 0, triangular meshes violate the maximum angle condition, leading to inaccurate approximations. Interpolating at 3 vertices or 3 mid-edge points results in nonconvergent area approximations, highlighting the limitations of these approaches. In contrast, nonconforming finite elements exhibit continuous functions up to the pk1 order, ensuring that the jump of two pk polynomials on two sides of an edge is L2 orthogonal to the space of pk1 polynomials on the edge. When applied to the cylinder approximation problem, P1 interpolation at 3 mid-edge points yields a slightly better approximation, but still fails to converge to the true solution. A novel solution to this problem involves moving the interpolation points towards the center, effectively creating almost tangent triangles. Alternatively, using the P1L2 projection of the cylinder function enables the total area of triangles to converge to the area of the cylinder. This approach ensures that the arc length of line segments converges to that of the circle as the mesh size approaches 0. By exploring these different approaches, the importance of carefully selecting interpolation points and projection methods is highlighted to achieve accurate approximations of curved surfaces using triangular meshes. This research underscores the need for a more nuanced understanding of the interplay between mesh geometry and interpolation techniques to overcome the limitations of traditional finite element methods. The finite element method is a widely used numerical technique for solving partial differential equations. However, its convergence relies on certain mesh quality conditions, such as the maximum angle condition. This paper introduces a novel weak Galerkin (WG) finite element method, termed PKWG, which can operate on arbitrary triangular and tetrahedral meshes without any constraints on mesh quality. PKWG employs a discontinuous finite element approach, eliminating interelement integrals and penalty terms in the discrete equation. This formulation makes the finite element solution nearly equivalent to the L2 projection. Notably, PKWG is the first method to guarantee convergence of finite element solutions on meshes without any quality constraints, marking a significant advancement in mathematics. The analysis of PKWG differs from traditional finite element error estimates. It involves converting interelement errors to intraelement errors and directly introducing local interpolation and projection to estimate the H1 projection error. A gradient-preserving Zhang transformation is also defined, analogous to a scalar version of the inverse Piola transformation. The PKWG method has important implications for mesh quality assessment and computational efficiency. It may allow for the presence of isolated poorly shaped elements, reducing computational costs. Furthermore, PKWG could benefit situations where mesh generators or adaptive algorithms would otherwise excessively subdivide a large region to avoid a single poorly shaped tetrahedron, potentially reaching computational limits. The weak Galerkin finite element method is a numerical technique for solving partial differential equations on an arbitrary triangular or tetrahedral mesh of size h on a polygonal or polyhedral domain omega. The weak Galerkin finite element space VH consists of functions VH equals V0, VB, that satisfy specific properties, including V0 being in L2, TH, and VB being in L2, EH, where EH is the set of all edges or face triangles in TH. The weak gradient nabla WVH is defined as an element of pk plus 1, T, D, satisfying a specific equation involving the inner product of nabla WVH and a test function Q, and the boundary terms involving VB and the outer unit vector n on E. This definition is rewritten using integration by parts, yielding an alternative form of the weak gradient. The weak Galerkin finite element method is applied to a model problem of Poisson's equation, seeking the finite element approximation in VH that satisfies a specific equation involving the weak gradient and the forcing function f. A key result, established in Lemma 2.1, states that the L2 norm of the weak gradient nabla WVH is bounded above by the L2 norm of nabla V0, with a constant C independent of the shape regularity and size of TH. The proof of Lemma 2.1 involves decomposing VH into two components, V1 and V2, and using the fact that V1 is a one-piece polynomial to establish the desired inequality. This result is crucial in establishing the convergence and stability of the weak Galerkin finite element method. The finite element method is employed in this study, where a general triangle or tetrahedron is mapped from a reference element T via an affine mapping F, with Jacobi matrix J, F. The mapped functions V0 and V2 are defined, and subsequently, two polynomials U0 and U2 are constructed on T using the Zhang transformation, a gradient-preserving transformation akin to the scalar version of the inverse Piola transformation. This transformation ensures that the gradients of U0 and U2 are related to those of V0 and V2 via the matrix M. The Zhang transformation allows for the derivation of an inequality, bounding the norm of the gradient of WVH in terms of the norms of the gradients of V0 and WV2. Specifically, it is shown that parallel nabla WVH parallel 2T is greater than or equal to 1 minus gamma, parallel nabla V0 parallel 2T, where gamma is a constant less than 1, dependent on the angle between the two finite-dimensional vector spaces. This inequality is then used to prove Lemma 2.1, which establishes a lower bound on the norm of the gradient of WVH. The proof involves summing the inequality over all elements T, thereby demonstrating the lemma. Subsequently, Lemma 2.2 is presented, which asserts the uniqueness of the solution to the linear system of finite element equations. The proof involves showing that if the right-hand side of the system is 0, then the solution must be 0. This is achieved by first demonstrating that is a piecewise constant function on the mesh, and then constructing a function Q that satisfies certain properties, ultimately leading to the conclusion that is continuous on the entire domain and equal to 0 due to the boundary condition. Theorem 3.1 establishes the convergence of the finite element solution to the Poisson equation, bounding the error between the exact solution and the finite element solution by a term dependent on the mesh size and solution regularity. The proof begins by testing the Poisson equation with a function from the finite element space, leveraging integration by parts and the weak gradient definition. This reveals the relationship between the exact solution and the finite element solution, introducing the L2 projection operator πk plus 1, which projects the exact solution onto the piecewise pk plus 1 space, and the local L2 projection operator qh, which projects the solution onto each element and face. The error estimate, given by equation 3.1, bounds the error between the exact solution and the finite element solution in terms of the mesh size and solution regularity. This estimate is derived through a series of manipulations, including the use of the weak gradient definition and the introduction of the IBDM gradient operator. The final estimate, equation 3.4, shows that the error between the exact solution and the finite element solution is bounded by a term dependent on the mesh size and solution regularity. Specifically, H parallel πk plus 1 nabla u minus nabla wa parallel 0 plus qh u minus a parallel 0 is less than or equal to chk plus 3 u k plus 3. This estimate provides a bound on the error between the exact solution and the finite element solution, a key result in the analysis of the finite element method. The result has implications for the practical implementation of the finite element method, guiding the selection of the mesh size and the choice of the finite element space to achieve a desired level of accuracy. The proof highlights the importance of the L2 projection operator and the weak gradient definition in the analysis of the finite element method, tools used to derive the error estimate and part of the theoretical framework underlying the finite element method. The mixed finite element method is applied to a second-order elliptic problem, and error estimates are derived for the resulting solution. The BDM interpolation operator, IBDM, is defined as a mapping from H1, T, D to BDM k plus 1, the space of BDM elements of order k plus 1. Three conditions ensure that IBDM preserves the normal component of the gradient on the boundary of each element, as well as the divergence-free property within the element. To derive error estimates, a combination of interpolation and consistency errors is employed. The interpolation error is controlled using local Taylor polynomials, while the consistency error is bounded using the standard full regularity assumption for the problem. The final estimate shows that the L2 error of the solution is of order O, h caret, k plus 3, where h is the mesh size and k is the polynomial degree of the finite element space. The proof involves applying the BDM interpolation operator to the solution U and its gradient, as well as utilizing the finite element solution WH for the auxiliary problem, 3.6. The interpolation and consistency errors are combined, and the full regularity assumption is applied to obtain the final result. This estimate demonstrates the optimal convergence rate for the mixed finite element method, highlighting the accuracy and efficiency of the approach for solving second-order elliptic problems. The derivation of the error estimates relies on a detailed analysis of the interpolation operator and its properties, as well as the application of standard finite element techniques. The resulting estimate provides a quantitative measure of the accuracy of the mixed finite element method, enabling researchers to assess the reliability and efficiency of the approach for solving complex elliptic problems. Numerical testing of the finite element method for solving the Poisson equation is presented through two examples. A 2D case on the unit square domain omega equals 0, 1, times 0, 1, with exact solution U equals 24, x minus x2, y minus y2, and a 3D case. The Poisson equation is given by equation 2.4, with forcing term f equals 25, y minus y2 plus x minus x2. Two families of meshes are employed, quasi-uniform and degenerate meshes, which violate the maximum angle condition as the mesh size h approaches 0. Quasi-uniform meshes, shown in Figure 2a, are used to test the convergence of the P1 conforming finite element method. The results, presented in Table 1, demonstrate that the method converges at the optimal order in the L2 norm and is superconvergent in the Semma 1 norm on these meshes. In contrast, degenerate meshes, shown in Figure 2b, are used to test the robustness of the finite element method. However, the results in Table 1 show that the method fails to converge to the exact solution when the mesh is refined more in one direction. Instead, the solutions converge to a different function, which is below the true solution. This highlights a limitation of the P1 conforming finite element method when using degenerate meshes, consistent with the theoretical analysis presented earlier, which showed that the maximum angle condition is necessary for the convergence of the finite element method. The numerical test underscores the importance of using meshes that satisfy the maximum angle condition to ensure the accuracy and robustness of the finite element solutions. The next step is to investigate the performance of the finite element method in solving the 3D Poisson equation, which will provide further insights into the accuracy and robustness of the method in higher dimensions. The authors present error profiles for the 2D P1 conforming finite element in solving equation 4.1 on quasi-uniform and degenerate meshes, as depicted in Figure 2. The computed error norms, parallel EHU-A parallel 0 and EHU-A 1, for varying grid sizes are displayed in Table 1. The data reveals a convergence rate of approximately 1.6 to 1.9 in the L2 norm and 1.5 to 1.6 in the energy norm, consistent across both quasi-uniform and degenerate meshes. Next, the authors compute the error profile for the 2D P1 weak Galerkin finite element, with k equals 1 in equation 2.1, on the same meshes. The results, presented in Table 2, demonstrate a convergence rate of approximately 3.8 to 3.9 in the L2 norm and 2.8 to 2.9 in the energy norm, again consistent across both quasi-uniform and degenerate meshes. Notably, this convergence rate is 2 orders above the optimal order. The authors then proceed to the second example, solving equation 2.4 on the unit cube domain omega equals 0, 1 times 0, 1 times 0, 1, with a specific choice of f given by equation 4.2. The exact solution to this problem is u equals 26, x minus x2, y minus y2, z minus z2. Two families of 3D meshes are employed, as displayed in Figure 3, with the top meshes being quasi-uniform and the bottom meshes being degenerate. Numerical results for the P1 conforming finite element method in solving the Poisson equation with the exact solution given by equation 4.1 demonstrate optimal convergence rates in L2 norm and superconvergence in SEMA 1 norm on quasi-uniform meshes, as seen in Table 1 and Figure 2. However, refining the mesh in one direction leads to non-convergence, with solutions converging to a different function below the true solution. In 3D simulations, quasi-uniform but non-nested meshes, Figure 3a, and degenerate meshes violating the maximum angle condition, Figure 3b, are examined. Table 3 displays the error profile for the 3D P1 conforming finite element method in computing solution 4.2 on these meshes. On quasi-uniform meshes, the method exhibits optimal convergence rates in both L2 and H1 norms. In contrast, on degenerate meshes, the method fails to converge, with the error stagnating or increasing as the mesh is refined. Furthermore, results for the 3D P1 weak Galerkin finite element method, with k equals 1 in equation 2.1, in solving the same problem are presented in Table 4, computed on the meshes depicted in Figure 3. This table provides additional evidence of the method's performance on different mesh types, highlighting the importance of mesh quality in finite element simulations. The results underscore the need for careful mesh design to ensure optimal convergence rates and accurate solutions. The paper presents the two-order superconvergence of a weak Galerkin finite element method on both quasi-uniform and degenerate meshes in three-dimensional space. Table 4 illustrates the error profiles for the P1 weak Galerkin finite element, demonstrating that the method is two-order superconvergent in both L2 norm and the energy norm. This is evident from the decreasing error rates with increasing grid size. In the ethical statement section, the authors declare that the submitted work is original and not published elsewhere. They confirm that no studies involving animals or human participants were conducted, and no datasets were generated or collected during the research. All authors declare no potential conflict of interest, and the funding sources are provided. The authors' contributions are equally distributed among them, and relevant ethical guidelines were followed throughout the study. This research contributes significantly to the field of numerical analysis, providing insights into the performance of weak Galerkin finite element methods on different types of meshes. The findings suggest that this method can be a reliable tool for solving partial differential equations in complex geometries, which is crucial for various applications in engineering and physics. The development of a stabilizer-free weak Galerkin finite element method for solving the Stokes equations on polytopic meshes is presented. This approach achieves order 2 superconvergence by employing unidimensional discontinuous finite elements. The authors provide a unified analysis of discontinuous Galerkin methods for elliptic problems, incorporating the angle condition in the finite element method and the mathematical theory of finite element methods. Previous research in this area is reviewed, including works by Arnold et al., Babushka and Aziz, Babushka and Zielamal, Brenner and Scott, Kruzex and Raviart, and Mu et al. These foundational studies have laid the groundwork for the development of discontinuous Galerkin methods for elliptic problems. The proposed method eliminates the need for stabilizers, which are typically required to ensure the stability of discontinuous Galerkin methods. This is achieved through the use of a weak Galerkin formulation, which allows for the construction of a stable and convergent scheme. The resulting method is shown to be highly accurate, with optimal convergence rates observed for both velocity and pressure fields. Theoretical analysis reveals that the method is robust and flexible, capable of handling complex geometries and boundary conditions. The authors also provide numerical examples to demonstrate the efficacy of the proposed method, showcasing its ability to accurately capture the solution of the Stokes equations on polytopic meshes. Overall, this study contributes to the advancement of discontinuous Galerkin methods for elliptic problems, offering a novel and efficient approach for solving the Stokes equations on complex domains.